The recording has started. Can anyone confirm? Am I audible? Is there anyone who can confirm? Okay, thank you. And the screen is visible, huh?
Yes, sir.
Thank you. Okay, then let's start. So, good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow with Department of Mathematics, IIT Patna. I am your NPTEL PMRF teaching assistant for the course Introduction to Probability Theory and Stochastic Processes. This course is offered by Professor S. Dharmaraja. He is a faculty in IIT Delhi. This is a 12-week course, and we are in the third week live session. Okay. So in the previous 2 weeks, we have discussed about the basics of probability and the random variable. Now, in this week, like in week one, we have discussed about like basics of probability. And in week two, we have discussed about the random variables, their properties, CDF, TNF, etc. Okay. Now in week three, we will discuss about the moments and inequalities. Moments and inequalities. Okay. So in which we will discuss like its mean and variance, which is usually first and second order moment. Then we will go for the higher order moments. Then we will discuss about some moment inequalities. Like Markov inequality, Chebyshev's, and then Jensen inequality is also there. And we will discuss about the generating function as well. Generating functions like probability generating function, in short, PGF, moment generating function, MGF, and characteristic function. Characteristic. Okay, so in this week, we will try to cover these things. So up to week two, if you people have any kind of doubt, please you may directly ask here. Okay, so let's start. So what is moments? Moments are like the quantity which specify the random variable or the distribution. Okay, that is called moments kind of thing. Like we have a different kind of image regarding our analysis. Okay, so in which the simplest one is mean and variance. So let's start with mean. This is usually denoted by like expectation of x also. So suppose x be a random variable. Suppose x be a random variable. Okay, over a probability space omega, let's say f and p. Okay, then in case x is discrete, in that case expectation of x. This is also called the arithmetic mean, expectation of x or first order moment. Okay, this can be defined as the summation x into probability that x is equal to x. So here this quantity, as you have already discussed, is the probability mass function. Okay, in short, PM. Okay, so this is defined as the moment or arithmetic mean or first order moment or expectation of x. Okay, in case x is continuous in nature, then in that scenario, then in that case, the expected value of x is just we replace the summation with integral x into here this fx is nothing but probability density function, in short PDF. Okay, so this is the formula for mean or arithmetic mean or average, okay, or expectation. Okay, just a second. Okay, so now actually there is one condition here. This exists if provided that like the mean of the absolute random variable, that is the mod x, probability that x is equal to x, is finite, or in case of obviously continuous random variable, if this is finite, in that case these terms, the expression defined above is nothing but the average value, the mean, the expectation of the random variable x. Okay, these have already been discussed. uh, like let me give you one example actually here. Suppose we are given a random variable which follow a distribution fx such that fx is defined as 1 upon pi 1 plus x square. Okay, for x belongs to real number. Suppose, okay, suppose, okay, this is one of the PDF. Okay, and the random variable x is there. Now we need to calculate the moment. We need to calculate the first order moment expectation of x. So before that, let us see whether this condition holds or not. If this condition holds, then we are able to calculate the expectation. Okay. Okay. So since it is a continuous random variable, we will use integral minus infinity to infinity modulus value of x, and then fx is nothing but 1 upon pi 1 plus x square dx. Okay. Mod x is an even function, obviously, we know. So it is even. So the integral is now from 0 to infinity. The twice is there. So pi, it's 2 upon pi, we will take outside. Then it's x upon 1 plus x square. Okay. Okay. I think up to this point, everything is okay. And yes. Okay. So when you are going to solve this, now you will find that it is actually a divergent sequence. Okay. So this is, so that means when you are going to solve this, you are not going to get a uh, finite quantity. Okay. So this is a divergent series or divergent function. So because of that, you are not able to calculate the expected value for this random variable x, which follow this fx 1 upon pi 1 plus x. Okay. So this is the case. So that's why we first need to find whether this quantity, this condition must hold to find the expected value of a random variable. In the same manner, for example, uh, suppose we have like the random variable x in such a manner that 2 to the power minus 2x. This is nothing but the uh, probability density function for the random variable, which is exponentially distributed. Okay, here x is greater than 0. Okay, and the 0 otherwise. So this is the PDF. In that scenario, suppose if we need to like calculate this function 2 into e to the power minus 2x dx, then in that scenario, again, mod x even function 0 to infinity is there, x is there, 2 to the power minus 2x dx is there. Okay, so obviously e to the power minus 2x, the like what? The series summation e to the power x formula we already know. Okay, then we will once put those formula, then we will get nothing but 1 by 2 here. Okay, that is, it's a finite quantity. So that means its uh, expectation value exists. Okay, so this is the meaning of expectation. Uh, we have some remarks here, some notes. We will discuss in fourth week actually about the different discrete and continuous distribution. Okay, where you directly know the mean and variance of some well-known distribution. Okay, so here the remarks will be like, suppose we need to calculate or find the expected value of some constant. Okay, so expectation of a constant is nothing but the constant itself. Okay, again, it also follows the linear property. That means expected value of ax plus b is nothing but expected value of ax plus expected value of b. Here b is constant, so obviously that comes out to be expected value of a into expected value of x plus b. Okay, in the same manner, suppose we are given a random variable x. Okay, and we transform another random variable y from the x only, y equal to gx. Then in that case, suppose we need to find the expected value of y, which is nothing expected value of g of x. Okay, so this is defined as summation x, which is gx probability that x is equal to the PMF. In case of continuous case, just replace summation with integral. Okay, because we know that if x is a random variable, then y, which is a function of x, is also a random variable. Okay, so this is the some of the remarks. There is one more remark actually. This is like, suppose we are given a continuous random variable. Suppose x, like it's a continuous random variable. Suppose x is a continuous random variable and we are given the CDF, the cumulative distribution function of the random variable x, CDF capital Fx. Okay. And if expected value of x exists, just if expected value of x exists, then in that case, this expected value of x can be calculated directly via CDF in with this formula. Okay, the integral over 0 to infinity 1 minus fx, which is also called as survival or reliability function. Okay, 1 minus CDF is nothing but survival or reliability function. So with the integral over 0 to infinity 1 minus capital Fx and minus of minus infinity to 0 Fx. Okay, so if in case we are only or directly given the CDF, we can use this formula to find the expected value of the random variable. But this only holds in case of continuous. Okay, so this is it. Now the variance. Variance is actually our second order moment. Okay, so actually we have to we have two kinds of moments. The first one is central moment and the non-central moment. Okay, so variance is actually second order central moment. Okay, so what is it? It's like, suppose we are given x, which is nothing but a random variable. Okay, we are given x is a random variable and its expected value of x exists. Okay, and let's see it's mu. Okay, then the second order moment about mean. Okay, so the central moment is actually moment about mean. Okay, or non-central is about, usually we are taking origin. Okay, these are a kind of nodes. Okay, and invariant it is second order central moment. Okay, so this is nothing but the second order central moment about, that is moment about mean. Okay, and the formula for the variance is v of x or var of x. Usually we will denote these things. This is nothing but the expected value of x minus expectation of x, the whole square. Okay, so this is the variance. Okay, this is variance. E of x is nothing but our mean, or we can write like this manner, x minus mu, because we have taken expectation of x is equal to mu. Okay, you can simplify via the a minus b whole square formula to this formula. Okay, and x minus mu whole square, x square plus mu square minus 2 mu x. Then we will apply expectation, because expectation is a linear, contain linear property. Okay, so it applies on all the things, like all the variables. And then after solving, you will get something like this. Okay, or you will get something like this: expectation of x square minus expectation of x whole square. Okay, here expectation of x square and expectation of x whole square are nothing but, this is actually non-central moment, non-central second order moment. This is our first order moment, that is mean actually, is our mean actually. Okay, so here, uh, from here we can like find out every non-central and central moments are connected with some relation. Okay. We will like write one more formula, a general formula for the non-central and central relationship. Now we will have some remark for this as well. So the mark will be like as variance of some constant. Uh, like in expectation case, the expected value of any constant is nothing but the constant itself. But in case of variance, the variance of a constant is nothing but zero. Okay. And the linearity property, variance of ax plus b is what? Variance of ax plus variance of b. Since variance of b comes out to be zero. And here, since it is actually a square term, so the scalar quantity comes out from the variance as it's a square form. It's a square variance of plus variance of b comes out to be zero. Okay, so this is the case. Also, variance of any random variable x is always greater than or equal to zero. It is a square term, so that means either zero or more than zero. Okay, so these are the three properties. Uh, yes, now the higher order moments will be like this is the general formula for mean and variance. Okay, for discrete as well as continuous case. Now the higher order moment. Okay, so for higher order moments, okay, let me write one more thing. The non-central moment usually denoted as mu dash r or mu dash n. Okay, for central moment is mu r or mu m. Okay, so for higher order moment, let me define the central moment first. The central higher order moment of we write it the rth order expected value of x minus expectation of x to the power r. Okay, and non-central case expected value of x to the power. Okay, so that is what? That is the non-central moment. We take the mean equal to zero. Okay, so that's why we will call the moment about mean and the moment about origin. So this is the general formula for the higher order moment, and the same formula for r equal to 1 and r equal to 2 we have discussed in the above. Okay, so this is the moments, and there is one theorem actually. Okay, there are some properties related to these moments. Let me write it in remark form or theorem form. So the first one is like if x is a random variable, if x is a random variable, such that we have a question on the basis of this remark only. Okay, such that mu dash r exist. Okay, then okay, let me write here mu dash n exists, then mu dash r exists for all r less than n. So that means what? If higher order moment exists, then all the lower order moment must exist also. Okay, so that means higher order moment exists implies the lower order moment exists as well. Okay, so this is one remark. And also there is one more remark. Okay, since we have discussed that, like there are relationship between the non-central moment and central moment. So there's a relation between those non-central and central moment, and it's like mu n, the nth order central moment, is defined as, it's for example, k equals 0 to infinity, and choose k. Okay, it's mu k dash, that is a kth order non-central moment, and minus of first order non-central moment, that is our mean n minus k. Okay, so this is the relationship between the non-central and central moment, that is mu n and mu n dash or mu k dash. Okay, so and this formula can be like derived from the binomial expansion of, suppose a plus b to the power n. So from there you can derive this formula like what, from even is like expectation of x minus expectation of x power n. So it's a minus b to the power n. Expand this with the help of the binomial expansion formula, and then you will find. Okay, you will find the above formula. Okay, so this is what moments are. Okay, now we will discuss about some inequalities. Moment inequalities is there. So here mainly 3 or 4 inequalities. The first one is Markov inequality. Suppose we are given a random variable, okay, and then we have information related to those random variable as well. Okay, that this random variable follow this distribution with these mean and variances and other quantities. Okay, but in case we do not have the complete information related to those random variable, then in that scenario, we have some partial information, obviously. Okay, but we do not have the complete information. Then in that scenario, we will use some inequalities to found a bound, a maximum, that is a maximum or a minimum value of probability or associated statistical quantity. Okay, so Markov inequality is one of those inequalities. What it does, okay, it gives the probability, it gives the upper bound of the probability when we have information of only the mean. Okay, only the expectation of x is given, that is only we have the average value, and then with the help of those average value we are able to formulate an upper bound for the random variable x. Okay, so in that scenario we will use a Markov inequality. So again, suppose we are given a random variable x. Okay, suppose x is our random variable. Okay, and here x is actually x is our positive. Okay, x is positive, or we can write probability that x is greater than or equal to 0 comes out to be. Okay, so both have the similar meaning. Okay, x is greater than positive, that x is a positive random variable, that is. Okay, or we can write it in the same manner, because probability that x is greater than or equal to 0 comes out to be 1. So that means what? The support of x is greater than or equal to 0. Okay, there is no negative value associated with the random variable there. So this is the case. Okay, also the expectation of x exists. Also, the expectation of x exists. Okay, so we have only expectation of x. I do not have extra information related to the random variable x. Then in that scenario, our probability that x is greater than or equal to k is less than or equal to the expected value of x upon the k itself. Okay, where k is any constant. Okay, so this gives the upper bound. This gives our upper bound of the probability. Okay, so this inequality, the Markov inequality, is used when we have only the average value, okay, and the random variable. Okay, so in that scenario, the probability that x, the random variable x, is greater than or equal to some constant k is always less than or equal to the expected value divided by its the constant itself. Okay, so obviously the maximum value lies either expectation of x divided by k or always less than that. Okay, so this is the Markov chain. Okay, in the same manner, we have Chebyshev's inequality. This is, sorry, not Markov chain. Sorry, it's Markov inequality. Now the next is Chebyshev's inequality. Suppose we have the average value as well as the variance. Okay, instead of the expected value of the random variable, we have the variability of the random variable as well. Then in that scenario, we will use the Chebyshev's inequality. Okay, and for that, obviously, we are given a random variable x. And we are also given the expected value of x. Let's write it as mu. We are also given the variance of the random variable. Let's write it as sigma square. Usually we will write. And these two are exist. That means first and second order moment exist. This means first order moment as well as the second order moment exist. Okay. Then for any k is greater than 0, for any k is greater than 0, we have something like this. Okay. We have something like the probability that modulus value of x minus mu, the expected value, x minus mu, is greater than or equal to the constant k is less than or equal to its sigma square, that is variance of x, and divided by the constant square k. Okay, so this is the yes, this is the Chebyshev's inequality. We can write it in other form as well. That is probability that modulus value of x minus mu, since it is greater than or equal to k, so we will write less than k. Okay, is less than or equal to, so we will write it greater than or equal to it's sigma square upon k square. So it's 1 minus sigma square upon k square. Simple, both are similar meaning. Okay, so this also gives the bound for this probability value that the x is deviated from their average value and the deviation is greater than or equal to k. This probability less than or equal to the variance divided by the square of the deviation. Okay, so this is the Chebyshev's inequality. So Markov inequality, obviously one of the special case of the Chebyshev's inequality. The next is Jensen inequality. Okay, so in Jensen inequality, again, we have a random variable and expectation of x exists. Okay, and we have now a transformed variable g. Okay, we have now a transformed variable g. So suppose x is our a random variable. Gx, let's say y, this is our transformed variable. Okay, and this transformed variable g as either convex in nature or concave in nature. Okay, this gx obviously a function. It may be either convex in nature or concave in nature. Okay. Uh, then we have like two cases. No? Case one is convex in nature. When gx is convex in nature, when convex gx, we write case one, when gx is convex, then in that case, the expected value of g of x is greater than or equal to the functional value of expectation of x. Okay, this is the case. And obviously, case second is something just reciprocal of this point when gx is concave. When gx is concave, in that case, expected value of g of x is less than or equal to the functional value of expectation of x. Okay, and you may know how to find the given function is convex or concave by using obviously first and then second order derivative. Okay, we will have one question on this topic as well. Even. Okay, so this is there is one more inequality that is actually we will not use, but let me write here. Lyapunov inequality. Okay, so this inequality is like suppose we are given a random variable and we have a function. Okay, this function is defined as the expected value of this. Okay, that means this must be exist. Okay, this must exist less than that infinity, less than infinity, that is finite. Okay, so then for any arbitrary k, then for any arbitrary value of k where k lies within 0 to n. Okay, then it will be like beta value of k minus 1 power 1 upon k minus 1 upon k minus 1. This is always less than or equal to beta k 1 upon k. Okay, so this is also a kind of inequality. So this is Lyapunov inequality. So these are the inequalities up to this point. Any doubt or any question up to this point, you people please ask here. If not, then we will go for the generating function. Okay, now the generating functions, we have three generating functions. Let me write the formula only. Okay, the first one is probability generating function, that is PGF. Okay, the PGF is where here x is our non-negative integer valued random variable, that is discrete. Okay, suppose x is our discrete random variable, okay, or non-negative integral valued random variable, and let me write pk for short probability that x equal to k for k equals 0, 1 to n. That means discrete random variable, and this is the probability mass function given. Then the probability generating function, the PGF, probability generating function, usually denoted as G, X, and the dummy variable S, is defined as the summation a from 0 to infinity probability of x equal to k into s to the power k. Okay, you have like you may able to recognize this structure. Actually, this structure is nothing but expected value of s to the power k. expected value of s to the power k into probability that x is equal to k. And we've taken summation. So that means what? It is our kind of expected value. So probability generating function is defined as the expected value of s to the power. Okay. We have some remarks. Remarks will be like the generating function value at s equal to 1 comes out to be 1. Okay. Then we have also like suppose the generating function value. Okay. We write some smaller version. The generating function. Okay. This r is actually our the rth order derivative. That is dr upon ds. Okay. The rth order derivative of the generating function. Okay, the rth order generating function. Okay, then in that scenario, this will give us actually the factorial moment. Okay, the factorial moment. So how it comes? Like g x of r s at s equal to 1. Okay, at s equal to 1 will give expected value of x, x minus 1, x minus 2, x minus r plus 1. This quantity is actually known as the factorial moment. This quantity is actually factorial moment. And since this generating function is associated with the discrete random variable, so you will definitely find in future that in some distribution case, we need to use these factorial moments to calculate the moment. Like for example, in case of binomial, even like when you are going to evaluate the second order moment, that is the variance. Okay, when you are going to evaluate the variance of the binomial distribution, then you will use this factorial moment concept here. Okay, so this is also be used. Also, it's like the next will be like probability value can also be calculated directly via the probability generating function. And this is defined as probability that x is equal to k. This can be evaluated like the generating function. Okay. Since x is equal to k is there, so kth order. Okay. Kth order derivative. Okay. At s is equal to 0 multiplied by 1 upon k factorial. When you are going to evaluate the probability at x is equal to k, then we will first differentiate the generating function up to kth order, then put s is equal to 0 and multiplied it with 1 by k factorial. This quantity will give the probability that x is equal to k. Correct. For obviously for k equal to like from 0, from 1 to n. Okay. Also, there is a like theorem actually sorry, not existence. It's a uniqueness theorem of PGM. Okay, the uniqueness theorem of PGM. So that means that says what? PGM. PGF is unique. Okay, so that means what? Since you have two random variable x and y, which follows fx and fy PDF. Okay, then if x is equal to y, then in that case fx is equal to f. That means if x and y both are not two different random variable, but a single random variable, in that case, the density function is also. So this gives the uniqueness theorem of probability generating function. Up to this point, if you people have any doubt, please ask it. Okay. Let me give you one example about the PGM. Okay. So suppose x is our discrete random variable. I'm going to like take the example of binomial distribution only. Okay. So as we people know, I don't know, we know or not up to this point because we have not yet discussed the discrete random variable, sorry, discrete distribution actually. So suppose x is a discrete random variable and we will have a probability mass function in that case, in that form. Probability that x is equal to x or x is equal to k will be like it's NCX, it's p to the power x. Let me write q. Q is nothing but 1 minus n minus x. This is all we know. Okay. Here p is here p lies between this. Okay. Q equal to 1 minus p and x equal to 0, 1 up to n. Okay. Then this is a probability and mass function for x random variable. So in that case, if I want to calculate the probability generating function, that is g x of s. So this is what? This is something like this. No? It's NCX, the PDF, the probability mass function value, p to the power x, q to the power n minus x, and obviously s to the power x. Okay. So this can be like written as like this. No? NCX, it's PS whole to the power x is q to the power n minus x. So this is now what? If you know, this is actually the extension, the binomial extension of what? PS plus q whole to the power n. So this is actually this function. This PDF is our binomial. So this is nothing but this is the probability generating function of binomial random variable. And binomial random variable is discrete in nature. Okay. So this is how you will calculate the probability generating function. The next, which is one of the most important, is moment generating function. Okay, MGF. The moment generating function is like it is defined as, usually it is denoted as MXT. Okay, this one is GXS. The probability generating function GXX. The usual notation, the standard notation is like this. The moment generating function MXT is defined as expected value of e to the power Tx. Here T is the dummy variable, obviously. This, or if you expand the e to the power Tx quantity, you will find like this: 1 minus e upon 1 factorial expectation of x plus t square upon 2 factorial expectation of x square minus it's t cube upon 3 factorial expectation of x cube and so on. Obviously, you can now understand this series. Okay, so this mxt can be expressed in this format, and from here you can see directly. No? You can directly see, no? This value, this value, this value. These are our non-central moments. So this is our moment generating function. That is, this function is generated via the help of moments, or this function is used to generate the moments. We can say anything. Okay. That means if we have moment generating function, we can directly use that function to find the moments. See? So this is moment generating function. We have some remarks of this moment generating function as well. The first one is obviously the expected value of x to the power n. That is the nth order non-central moment. The nth order non-central moment is like calculated directly by differentiating the moment generating function to the nth order. Okay. It's mxt and then put t equal to 0. See? Okay, you can take any order, first order, second order, third order, seventh order non-central moment, and that can be calculated by directly differentiate the moment generating function to the seventh time and then put t equal to 0. This will give the seventh non-central moment. Also, similar to the probability generating function, MGF is also unique. MGF, moment generating function, is also unique. Okay, so uniqueness theorem of MGF is also there. Okay, suppose two variables have the same MGF, then that variable is nothing but same or comes from the same distribution. The third, which is the last perhaps, the characteristics function. Okay, this is usually denoted by phi xt or psi xt. Okay, we write it phi xt. Okay, so it is actually expected value of e to the power itx. Okay, the moment generating function is defined as e to the power tx, and the characteristic function is defined e to the power itx. Okay, here I is our what? Iota, that is under root of minus 1, the complex. Okay, and t belongs to the whole real number. Okay, so it also has some remarks or some properties. Let me write it. The first one is like this EGF CF, that is characteristic function, sin xt, at t equal to 0 comes out to be 1. This is the first like property of the characteristic function. We also have like it's bounded actually. Phi xt is bounded in -1 to +1. Okay, so the value, the absolute value of this function is always less than or equal to. The third one is like if expectation of x to the power n exists. So that means what? Nth order non-central moment exists. In that case, this can directly be calculated via the characteristics function and putting the t equal to 0 multiplied by I to the power. Okay, the same thing. You can write like you can see this. The remark one of the moment generating function is actually equivalent to the remark of the third remark of the characteristics function, just multiplied by 1 by I to the power n. Okay, so similarly, as moment generating function is unique, our characteristic function is also unique. Okay, actually, when you have moment generating function, then you can directly replace tx with itx. Then that is our characteristics function. Okay, so this is it. If you have any doubt up to this point, you people may ask. If not, then we will solve some numericals based on this topic. Any doubt? Am I audible now? Let me confirm at least this.
Yes, sir.
Okay, thank you. Okay, then we will solve some numericals based on this. Okay. So our question will be like, let x be a constant random variable. Okay. Let x be a constant random variable. Then variance of c is actually the constant, is, we need to find the variance of constant. As we have already discussed, the variance of constant is nothing but zero itself. Okay, so but let's solve this. Okay, let's solve this. Since we know that, what is the formula for variance? Variance of x, variance of a random variable is like what? Expected value of x minus expectation of x whole square. Okay, this is the case. Since like c is constant, since c is constant, so that means what? Expected value of c comes out to be c. We have already discussed the properties of expectation. The expected value of a constant is constant. I think someone has asked something. Zero. Okay. Yeah, you are right. Zero. The expected value of c is c here. So the expectation of c is c. So that means our variance of x is what? Expectation of c minus expectation of c whole square. That can be written as like something c minus expectation of c comes out to be c whole square. Obviously, expectation of 0 so comes out to be 0. This is obviously used when you have like subjective examination. So you need to know how we will prove or solve. So the variance of any constant variable is nothing but constant. Sorry, 0. Okay. There is a second question. This question is good. Like, consider a scenario. Consider a scenario where two teams, team A and team B, are competing in a series of games. Are competing in a series of games. Okay. Uh, each game is independent. Each game is independent. So that means the outcome of one game does not affect the outcome of the another. Okay. Each game is independent means outcome of one game doesn't affect the outcome of other. The first team to win, the first team to win two games, to win the games will be declared. Okay. Sorry. Written question. Okay. The question will be the first team to win games. The first team to win game. The first team to win two games. No? The question will be like the first team to win two games will be declared the winner. Will be declared the winner of the series. Winner of the Nikhil. Okay. Now we have some information. The probability of team A winning, the probability of team A winning a game is winning a game is 40%, while for team B is 60%. Okay, this is given. Now let me write on the next page. Determine the expected number of games determine the expected number of games that will be played in the series. Okay. Determine the expected number of games that will be played in the series. See, if the player have the similar kind of probability, then in that case, you people have kind of logic that 2.5 number of games will be there. Okay. But here, since the probability is different, okay. So in that scenario, the solution of this will be somewhat different from the 2.5. So let's solve this. You people are also requested to solve by the rule. We are given what? We are given okay, let me change the color. We are given probability that team A win is 40%, that is 0.4, and the probability B will 0.6. That there is no tie and all. Okay. So this is we are given. And since it is mentioned, the team which own two games will win the series. Okay. So there are possibility that the series has either two games or three games, because when it has two games, then suppose team A win the first game as well as the second, then team A win the series. Okay, and vice versa, team B win the first game as well as the second game, then team B will win the game, will win the series actually. Okay, but in case suppose first game is is won by team A and then second game is won by team B, then there will be the third game which will be the deciding game, that which team will win the game or the series. Okay, so like we have two cases actually. Okay, we have like two cases. So that case will be before that, let me write. Here you can understand either there will be two game or there will be three game. Okay, so that means if n be the number of games, then possible value of n will be what? Either two or three. Okay, so now let me write case one. Suppose there will be two game only. Okay, series end with two games. Okay. Now, suppose two games. So in that scenario, what happens? So either team A will win the both the game or team B will win the both the game. Okay. So that means what? Team A, okay, wins both the game. Okay. And eventually the team A will win the series. Okay. So if team A will win both the games in that scenario, what probability that A, this is the notation for first and second game, both will be won by both will be win by the team A. And since we are also given each game is independent, so that means what? We can write like this, na? Probability of A into probability of A. And probability of A is given 0.4 into 0.4 comes out to be 0.16. Okay. So the probability that both the first and second game will be win by the team A is 0.16, that is 16%. Okay. Now, if the second scenario, if team B wins both the game, in that scenario, the probability will be like probability like this. It's 0.6 multiplied by 0.6, that is 0.6. So that means 36% chances that team B will win the game in the series when the series ends in 2 games. But the case second is also there. Okay, up to this point, it is okay. So that means what? Probability. So that means what? The probability that game ends in 2 games. Okay, the series ends in 2 games is actually what? Probability of this plus probability of this. So this comes out to be 0.16 plus 0.36. So probability that the game will end in 2 games only, the series will end in 2 games only will be uh, 0.5. That is 52% chances that the game will end in 2 games. The series will end in 2 games. Okay. Now there is a second case. The second case will be if there is 3 games. Okay. So like the series end in 3 games. Okay. So in that scenario, 2.44, someone has responses. Akansha has responded. Okay. Let me solve this. I don't have the final answer actually here. Okay. So it will be like either first game will be like the first game will be won by team A, then team B, or the team B and then team A. Okay. So in that scenario, the first case, the first game given by like A and then B. And then I don't need to write A or B because the game will definitely won by either team A or team B. I need to check the first and then the second one. Okay. So probability that this is actually probability of A into probability of B, as these are independent in nature. So it's 0.4, 0.6, it comes out to be 0.2. Similarly, probability of B, A. See, why I have not written A, B, A or A, B, B or this kind of, because our aim is to find out that series will end in 3 games. This will be like end in 3 games. Na? So obviously after that, the 1 game and one team will definitely win. So that's why this is the case. Okay. So this is probability of B plus probability of A, which is again 0.6 into 0.4, 0.24. Okay. So the probability that the series will end in 3 games is probability of AB plus probability of BA, which is 0.48. 0.24 plus 0.24 comes out to be 0.48. And you can see probability that also, like for verification, you can see probability that n equal to 2 plus probability that n equal to 3 comes out to be 0.52 plus 0.48 comes out to be 1. So that means this n, the random variable n that we have defined just in this question, is a valid random variable because the probability value comes out to be 1. It's a valid probability. Okay. So now the next is what? The next is expected value. Na? We need to find the expected number of games. So expected number of games will be like what? Like expectation of n is what? Like it's a summation n into probability that n equal to n, and n comes 2 and 3. So that means what? 2 into probability that n equal to 2 plus 3 into probability that n equal to 3. So 2 into 0.52 plus 3 into 0.48. So it comes out to be 1.04. Okay, not 0, to 104. Yes, 1.04 plus 48 into 3, 1.4. Okay, so it comes out to be expected value of n uh, comes out to be 2.4. Okay, so someone has answered. Yes, Nikhil, you have solved the right answer 2.48, and Akanksha has 2.44. You have missed 0.04. Okay, so just check where you have missed. Okay, so this is the final answer. I hope you people have understand how we have solved this. If you have any doubt, please let me know. Okay, then we will. Okay, so let me know when you have any kind of doubt. Now the next question is, we are given a random variable. Consider consider a random variables. Consider a random variable whose PDF whose probability density function PDF. Yes, someone has. Okay. Okay. Whose PDF is given by this PDF is given by this fx is 1 by 4 for x lie within -2 to 2. Find the moment generating function. Okay, that's simple question. Actually, you can see in next class. Obviously, we will discuss about the uh, some discrete or continuous standard distributions. Okay, then there you will find that this fx is nothing but the uniform distribution with the parameter -2 and 2. Okay, so here since we don't know, let's solve. So we need to calculate the PDF. Sorry, MGF. No, we need to calculate the MGF. So what we are given here, x follows our fx is 1 by 4 or -2 to 2. This is given actually. Okay, this is given. Now we need to find the MXT, and this is defined as expected value of e to the power tx. Okay, so it is a continuous in nature. So definitely we will take this integral minus infinity to infinity e to the power tx into fx dx. Since this range are given, the support for the random variable x is given -2 to +2. So it will be like -2 to +2 e to the power tx into 1 by 4 t. Okay, so 1 by 4 obviously comes outside from the integral. So it's -2 to 2 e to the power tx. Again, if someone has said 1 by 4 t e to the power 2t minus e to the power -2. Okay, let me write. Then I think that's the right answer. Okay, but let me correct it. Okay, so this is not again. Since we know that e to the power tx, that this comes out to be what? E to the power tx will be like, if you know, e to the power tx upon t. Simple. That we already know actually. Okay. But here t must not equal to 0. Just give me a second. Okay. This we already know. Okay. So what we are going to do is this mxt is like 1 by 4. It's e to the power tx upon t. Okay. E to the power tx upon t, it's minus 2 to. So it comes out to be like 1 by 4t, and it's e to the power, it's 2t minus e to the power minus 2t. Yes, I think you have written the right. Let me see. The previous question, we could have also used a complement to find the probability that series last 2 games, since it can only last 2 games or 3. Yes, you can obviously use, yes, directly, yes. You are right here. Uh, okay, let me discuss. Because here, the probability that the series will like last in 2 games as the probability 0.52, then undoubtedly it will give like 1 minus for 3 games, because there is only 2 exhaustive events for the value of n, or n equal to either 2 or n equal to 3. In that case, yes, you are right. Okay. Now, this is the case. Okay. So, this is the MGF. This is our moment generating function. Okay. This is our moment generating function. Okay. Now, if you want to check whether this moment generating function that you have just calculated is a valid or not, or it's true or not, then for that you have some properties, like the mxt value at t equal to 0 comes out to be 1. Okay. The mxt value at t equal to 0 comes out to be 1. And you will find, then you need to use the L'Hospital rule to find out whether this is actually like actually what I really wanted to say is this: to verify, you need to, like, mxt comes out to be, it's like this property. Okay, you need to verify this property as well. Okay, in examination especially. Okay, make sure that you have calculated correctly. There is no calculation error and all. Okay, so this can be calculated, but here you can see, if you put t equal to 0, you will find 0, 0 by 0, that is indeterminate. Okay, so you need to use the L'Hospital rule, and then you will find the limit t tends to 0 comes out to be 1. Okay, I'm not going to verify this. This is true actually. Okay, now the next question is like, just a second. Okay, now the next question is, uh, suppose we are given a random variable. Let x be a random variable. The x is a random variable which follow the PDF fx, with fx is given as like 2 e to the power minus 2x. That is the exponential distribution. or x is greater than 0, otherwise. Okay, so we are given this PDF. Now we need to find the characteristic function. Like calculate the characteristics function. Okay, so again we know psi xt or phi xt, whichever you would like to write. Okay, so we know that the characteristics function psi xt is defined as expected value of e to the power itx. Okay, where I is the iota, that is under root of -1. Okay, so integral minus infinity to infinity e to the power itx multiplied by the PDF. So the PDF will be 2 e to the power minus 2x here. Okay. Okay. You can write 2 equal to some other quantity in general, or you can take the value 2 itself. Okay. Since I am directly using to like usually we will use lambda or theta. Okay. Instead of 2, the parameter lambda e to the power minus lambda x, and for lambda equal to 2, this is the equation. Okay. So obviously from here you can see what you can, like we can see here is like 2 obviously can be taken outside from the integral. Then all the quantity will be like it's from 0 to infinity. No? So 0 to infinity. So, so it will be like e to the power itx and e to the power minus 2x. So if I take minus x is taken as common, so it will be like must be written later. So it will be like 2 minus it. Dear, simple. Okay. E to the power minus 2 minus it. E to the power minus 2 minus it x dx. So again, the same e to the power this. So it's the 2 is here. So it will be like, yes, it will be like minus of e to the power minus 2 minus it whole divided by 2 minus. Okay. 0 to infinity. Putting the value infinity minus of e to the power minus, here x is also there obviously, 2 minus it, infinity is there obviously, 2 minus it can be taken outside, minus e to the power minus of 2 minus it, 0 is there. So obviously you people directly know this value comes out to be, this value comes out to be like what? 0. And here actually it, here it comes out to be 1 because this minus this. So minus and minuses comes out to be plus, and this value 1. So from there 2 upon 2 minus it. This will be our final answer. Okay, this will be our final answer. So that means what? Phi we have used. Sin xt comes out to be 2 upon 2 minus it. This is the characteristics function for the random variable x when x follows the exponential distribution with the parameter 2. Okay. In case of lambda, just replace 2 by lambda. Okay. Up to this point, any doubt? Okay. So let's go to the next question. So, okay, I think someone has question 2 divided by 2 minus I. Yes, Nikhil, you are right. Okay, the next question will be like, we are given a discrete random variable. Okay, let x be a discrete random variable with the following probability mass function. So we are given the probability mass function in this manner. Suppose 1 by 6 when k equal to 0, 1 by 3 when k equal to 1, 1 by 2 when k equal to 2, and 0 otherwise. This is the probability mass function we are given. Okay, now we need to find the probability generating function. Okay, we need to calculate the probability generating function. Okay, try to solve this by yourself as well. Okay, so am I audible? No? Can anyone confirm?
Yes, sir.
You? Okay, so see, we need to find the PGF. Okay, so the PGF, as we have already GXS, the standard notation we will use this. Okay, it is expected value of s to the power k. Okay, and the expected value of s to the power k is like what? K from 0 to 2. Okay, because k equal to 0, k equal to 1, and k equal to 2 is there. So from 0 to 2, it s to the power k into probability that x is equal to k. So for 0, s to the power 0 into probability that x equal to 0 plus s to the power 1 into probability that x is equal to 1 plus s to the power 2 into probability that equal to 2. So it's s to the power 0 comes out to be 1 on probability that x is equal to 0 is actually 1 by 6. So it's 1 by 6 here plus s and probability that x is equal to is like 1 by 3. So s by 3 plus s square by 2. Okay. So this is our the generating function. This is our generating function. Okay, just as simple. For the valid, whether we need to either check whether this PGF is actually valid PGF or not. For verification, you need to check GXS at s is equal to 1 comes out to be 1. Okay, so you can directly check. Na? What we given? It's 1 by 6 plus 1 by 3 plus 1 square comes out to be 1 by 2. So obviously, it's 12 by 12 comes out to be 1. Okay, so this means it is a valid generating function for the given period. Okay, so any doubt up to this point? Okay, next question is again one property. Okay, we will prove that property. The question will be like, let X be a continuous type of random variable. Let X be a continuous type random variable such that expected value of X to the power R exists. Okay. Then select the correct one. Okay. So we are given 4 options actually here, and we need to select which one is the correct. The first one is expected value of S exists for all S is less than R. The second one is expected value of X to the power X exists for any S is less than R. The third one is expected value of X to the power X exists only for some S less than R, and the D will be like expected value of X to the power X exists. Sorry, it's not exist. It's may or may not exist. May or may not exist for S is R. Okay. Okay. Someone has some message. A is correct. Okay. Actually, yes, this is the correct, but we need to prove. Na? We need to prove that A is correct or not. How can we directly say that it is correct? So the right answer is obviously the option A is the correct one because we have already learned this as a property. So let's prove this. Okay. So we are given this, we need to prove. So see, since we are talking about the expected value, na, the moments, okay. So let me first introduce like this random variable X as either this or this. Okay. Is it okay up to this point? The modulus value of X is either less than or equal to 1 or greater than 1. Okay. So let's start with the less than case. Okay. So for less than case, suppose modulus value of X is less than or equal to 1. Okay. All since we are given S is less than R, in all the case we are given S is less than R. Okay. So we take a quantity S which is less than R, and uh, we know that X to the power S is also less than or equal to R. Is it okay? Since modulus value of X is less than or equal to 1, so obviously any power for on that is also gives less than or equal to 1. Okay. Up to this point it is okay. So that means what? So that means the expected value of X to the power S, when the suppose the functional value, we have considered the case when modulus value of X is less than or equal to 1, is less than or equal to 1. So that means what? These are just indicator. These are just for indication only that we have considered this case, and in this case, this this must less than 1, less than or equal to 1. So that means what? So that means what? That means expected value of modulus value of S I of X is less than or equal to 1 is finite. Okay, that means it can be solved. It is finite. Okay. Now the second case. Okay, so it is finite. Now the second case. Second case will be like what? Modulus value of X is greater than 1. Okay, and also we are given S is less than R. We are given. So from here we have what? X to the power S is also less than or equal to X to the power R. It is okay because X modulus value of X is greater than 1. It's more than 1. So obviously the power S is always less than or equal to power R because S is less than R. Okay, so this obviously true. So that means we can say the expected value of modulus value of X to the power S is greater than case, no? Greater than 1. Okay, this is always less than or equal to the expected value of this. Okay, this is the case. Fine. And we are given what we are given. This exist means that is finite. Okay, that has some form, some values. Okay, also like what we are given, like the expected value of X to the power R is finite. Okay, that means it exists. So from there what we can conclude, from this point we can conclude the expected value of modulus value of S this is also finite. Okay, so here you can see for X the modulus value of X is less than or equal to, for modulus value of X less than or equal to 1. In that scenario, it is less than 1, which is finite. Or greater than case also, it is finite. Or greater than case also, it is finite. So two finite number can be sum and it's a finite. Okay. So this implies what? Combining star and double star, we can conclude the expected value of X to the power S is finite. Okay, and in all this proving, we only take one condition that S is less than R. We do not impose any other condition for any specific value. Okay, so that means for any value of S, that means not for any, that means for all value of S less than R. So that means what? This is true for all value of S which is less than R. Okay, so this is how we will prove. So this implies that the if the higher order moment exists, then the lower order moment must exist as well. Okay, so that means X, the expected value of X to the power R exists. This implies X to the power S exists for all value of S less than R. So this proves the theorem. The theorem, the property was. Okay, any doubt how we have proved this? Then please let me know. Anyone any doubt? Okay. Okay, then we will go for the next question. Please let me know. No? If you people have any doubt, please let me know. Okay. Now the next question uh, It's based on the inequalities, obviously. We are given consider 100 students who gave the NPTEL exam. Consider 100 students gave the NPTEL exam with scores between 0 to 100. Okay, with mean 50. With an upper bound. Now the question is an upper bound on the probability that a student gets a score with the 78. Simple question. We are given 100 students. They gave the NPTEL exam and of marks 100, obviously. The average value comes out to be 52. Now we need to find the upper bound for the probability this. Okay. See here, what we are given, you can obviously read the question that here we are only given the average value. Okay, the average value of the exams and nothing else we are given it. Okay, we do not have any kind of knowledge whether which kind of distribution it is, which kind of marks is distributed, like more marks is less than 20, less than 52 or more than 52 or what. We do not have any kind of idea. Okay, that can be, we will read probably in the uh, 7th, 8th maybe lecture, or where we will discuss about the descriptive statistics. Then we will we will discuss the skewness and kurtosis and what is the interpretation of mean, median, mode, skewness, kurtosis. All. Okay, but here we are only given the mean value 50. Okay, we do not know whether the more value is greater than 52 or the more value is less than 50. Okay, most of the students lie within. Okay, we do not have any idea. Now the question is this: we need to find probability that x is greater than 70. Okay, so what we are given? First, let me write the given. Here we are given the random variable x, which is actually nothing but mass. Okay, this is given. You also please solve and let me know the final answer. Okay, so this is the random variable. Also, we are given the expected value at x is 52. The number of students involved in the exam is 100. So that means what? X belongs to 0 to 100, including both, obviously. Someone has responded. We will use the Markov inequality here. Answer will be 2 by 3. Okay. Yes, answer will be 2 by 3 perhaps. But yes, Markov inequality because we have only the average value. So it is correct up to this point. Okay. So the next is, since we are only given average value, so we will use Markov inequality. So Markov inequality will be like this. Na? The probability that x is less than equal to sum a is less than or equal to the expected value divided by the quantity. So let's put this together. So we need to take the probability that x is greater than equal to 78, less than equal to 52 upon 78. It can be calculated 13.4 upon 6. Yes. 2 by 3. Okay. So the probability comes out to be 2 by 3. So that means what? That means probability that X is greater than or equal to 78 is less than or equal to 2 by 3. See, what we can interpret, always try to interpret actually as a, okay, here you can see that the student 0 to 100 mark paper is there, okay, and 52 is the average. Since 52 is the average, then that means what? 2 by third of the student, this is the upper bound, always try to see this. This is the upper bound that the 66.67% of the student scored less than 78%, sorry, more than 78%. This is the bound. Okay. That means no 70% or 72% student will get 78 or more marks. Okay. If I need to know whether how many percentage of student will get 80%, 80 marks, okay, out of 100, then I am 100% sure that value must be less than 65% or 66%. Okay, because 78 or more than 78% of the marks will be scored by a maximum of two-thirds of the student. Okay, so this will give us an idea, a bound. Okay, and this is what the probability distribution is. Okay, if we have some information, some more information, then we will definitely have like a better result. Okay, but here we have a bound. Okay, the next question. Up to this point, is it okay? Okay, so the next question will be like one question related to the Chebyshev, obviously. Suppose a fair coin is flipped, we are given. Suppose a fair coin is flipped 100 times. Find the bound on the probability. Find bound on the probability that the number of times the coin lands on head. Lands on head is at least 60 or at most 40. Okay, so at least 60 or at most 40. We need to find it. Also, since here we are given a fair coin, okay, so that is actually the keyword here. Okay, from the help of the fair coin, we will find the mean and variance. Actually. Okay, actually this question can be solved via Bernoulli distribution as well. And if we are able to calculate the mean and variance of this random variable defined in this question, okay, then we can use a Chebyshev's inequality as well. Okay, so here we are given the bound, so we can directly use the Chebyshev. Okay, but before that we need to find the mean and variance. Obviously, here since a fair coin is tossed, so that means what? Bernoulli distribution. Here's a random variable x is what? X. Okay, so the number of x will be the uh, random variable. Number of x in 100 tosses. Okay, so the number of heads will be the our random variable. So obviously, the number of heads will be comes from 0, 1, 2 to 100 only. Okay, so here probability that head will occur, everyone know because it's a fair coin. So it will be 1 by 2 probability. Okay, also here this random variable x follows the binomial distribution with uh, n equal to 100 because we trial this experiment 100 times and the probability of getting head is 1 by 2. So this is our distribution. Since this can be like, if you people do not understand, this can be obviously understand in the next section, in the next lecture, but let's see here. Okay. When x follows the binomial distribution, the expected value of x is actually np. This is n and this is p. So it's 100 into 1 by 2 comes out to be 50. And variance of x equal to n p 1 minus p. It's 100 into 1 by 2 into 1 by 2 comes out to be 25. Okay. So we are given, now we are given mean and variance. If you can see, you will find mean and variance are given. Okay. Now we will solve this question. Also, we need to find at least 60. At least 60. So this can be written as like this. Na? This can be written like this. And at most 50. At most 50 will be like what? 50 minus x is greater than equal to this. So we will use the modulus value. Okay. 1 by 4 is the answer. Yes, 1 by 4 is the right answer actually. So you can understand. Na? So using the Chebyshev's inequality. Using the Chebyshev's inequality, what we can write? Probability that x minus mu is greater than or equal to a is less than or equal to sigma square upon a square. Simple. Now put the values. So probability that x minus 50 is greater than or equal to 10 is less than or equal to sigma square is equal to 25 upon a square is, and 10 square comes out to be 100. So probability that x minus 50 is greater than or equal to 10 is less than or equal to 1 by. So just try to imagine. Just try to imagine this. Okay. So the probability that the value of x, okay, the value of x is more than at least 60, more than 60 and less than 40. Okay. The probability that the number of heads in a course of 100 coins, okay, the number of heads is more than 60 and less than 40. This has only 25% probability. A maximum probability is 25. Okay. So that means more 75% of the time, the number of heads, when we toss a coin 100 times, the number of heads will lie within 40 to 60 or the 75% of the time. Okay. This is also one of the conditions. Okay. So you need to always try to interpret, at least understand the physical meaning of the probability. Okay. So up to this point, any question, any doubt? Anyone have any doubt? I have one more question. It's actually based on the Jensen inequality, and that is nothing, just proof. So I'm not going to prove that. Okay. We have already known in case of convex and in case of concave, we have a different approach. So that is the question. So if you people have any doubt or want to ask anything, then we can discuss. If not, then we will conclude our session here. Anyone? Okay. Am I audible now? Please let me know this.
Yes, sir.
Okay. So anyone have any doubt? Okay, I don't think you people have any kind of doubt. So let's stop here. Okay, we will conclude our session here. Thank you, everyone. Let me first stop the recording.